Okay, first one more example about finding maximum power transfer. Yeah, now we have this circuit, the ZL here connected to independent power, to independent voltage source, 24 volt and 12 volt, and there are three passive components: 2 ohm resistor, J2 ohm inductor, and minus J2 ohm capacitor. Find the ZL for the maximum average power transfer. In this case, we use this first condition, as we had learned earlier, that the optimum impedance should be the equals to the conjugate of the Thevenin equivalent impedance. Then second question is compute the maximum average power supplied to the load. You can calculate using this formula. PL max will be equal to half of the VOC, yeah, the open circuit of the Thevenin equivalent circuit to the terminal of the load squared, yeah, divided by 4 times the RTH, the real part of the Thevenin equivalent impedance. Okay, so when the load is taken out, this is what we have. So we have to calculate the impedance first, the Thevenin equivalent impedance, and the VOC. Okay, to calculate the VOC, here you can use two loops, yeah, loops analysis. First loops here, yeah, 24 plus 20 plus 12 equals to 36 equals to 2 plus J2 current times the current. Okay, then it means then the current will be equals to 36 times 2 minus J2 divided by 8. Yeah, the current here equals to this one. Then this equals to 9 times 1 minus J, or equals to 12.73 with a phase angle of minus 45 degrees. Then the open circuit will be equals to this voltage, yeah, which is minus 12 plus J2 times the current. Minus 12 plus J2 times the current is 1, 9 times 1 minus J. So when we obtain minus 12 plus 9 equals to 6, then the imaginary part is J2 minus 9J. Yeah, J2 times 9 equals to J18. J18. So from here, then the open or in phasor format, this is equals to 18.974 volt with a phase angle of 71.57 degrees. Then we find the ZTH. So the VOC square here is equals to this one, yeah, 6. This is calculated from here. 6 square plus 18 square equals to 360 degrees. So ZTH is found by short circuiting the voltage source. This is short circuit. This is short circuit. Is here, and the impedance, equivalent impedance, is seen from these terminals. So basically equals to this minus J2 ohm plus the parallel of 2 ohm plus J2 ohm. J2 ohm plus 2 parallel J2 ohm. Okay. Then and we find it equals to this one minus J2 plus 4J 2 times, yeah, 4J divided by 2 plus J2. And we simplify further. This equals to the ZTH equals to 1 minus J ohm. So then the Z optimum of the load should be equals to the conjugate of this ZTH, or 1 plus J ohm. Then the power maximum when the ZTH equals to the conjugate, when the Z optimum of the load equals to the conjugate of the ZTH will be equals to half times the VOC square, 360, divided by 4 times RTH. RTH is the real part of the ZTH, which is 1 here. So 4 times 1. So then the maximum average power supplied to the load should be equal to 45 watt. Okay. Then last example here, I think, for this maximum average power transfer. We have here another ZL connected to two independent voltage source, 24 and 12 volt also, with three passive components. Again, using the same formula to calculate for the optimum ZL, it should be the conjugate of the ZTH, and the maximum power average power transfer when ZL is optimum. So first, we disconnect ZL and try to find the open circuit voltage at the terminals. So using nodal analysis, okay, the Vj2 here will be equals to voltage divider formula from this 24 here, J2 divided by J2 minus J2 plus 2. So basically this is in series, okay, in this loop, times 24. So this equals 2, so this cancel each other, J2 divided by 2, okay, or J24, or basically 24 volt with a phase angle of 90 degrees. Okay, then using KVL at this, we can calculate VOC. Yeah, VOC will be equal to this 12 volt plus Vj2, or 12 volt plus 24 90 degrees equals to 12 plus 20 plus J24 volt in complex format. Then the VOC square will be equal to 12 square plus 24 square, or 720 volt square. Then we calculate the ZTH seen from the terminal. We short circuit, yeah, this source, voltage source, also we short circuit this voltage source. This is what we obtain. So this is basically J2 ohm in parallel with the series of 2 ohm and minus 2 ohm minus J2. Okay, J2 in parallel with 2 minus J2. So this is the result, and we simplify further to obtain ZTH equals to 2 plus J2 ohm. So hence, it means that the Z optimum for the load will be equal to the conjugate of this ZTH, or equal to 2 minus J2 ohm. And the maximum average power transfer to the load, supplied to the load, will be equal to half times VOC square, or 720, divided by 4 times RTH, which is 2 ohm here, 4 times 2. 720 divided by 16 equals to 45 watt. Okay, so when solving, of course, problems during the quiz or exam, yeah, you don't need to derive again this formula, you just need to memorize it. But of course, it is good if you know the derivation as we have derived in one of the earlier slides. Okay, so that then in case you forget, you can re-derive it. But I think this condition is easy to remember. Yeah? The optimum load impedance should be the conjugate of the equivalent Thevenin impedance. Only this may require a little bit of understanding of the derivation. So that the maximum average water transfer supply to the load will be equal to half VOC square divided by 4 times the real part of the Thevenin equivalent impedance. Okay. Any questions regarding the maximum average power transfer? If not, then we move on to another concept of effective or RMS values. Yeah, I think which Nikki had asked earlier. So basically, effective values or RMS value, root mean square. Root mean square, why is it called as root mean square? Because it is the formula how we obtain the effective, as we will explain later. Effective means that the equivalent, the effective value is the equivalent DC value that will supply the same average power. So the criteria here is they have same average power. Then what will be the effective value of the parameter voltage or current in DC, the equivalent DC. So as we know that in DC circuit, the instantaneous power PT across a dissipative component like resistor will be equals to PT equal to I square T times R, the instantaneous current being squared times the value of the resistance. Okay, so then if the current is sinusoidal, the current flowing here is sinusoidal, and we have done the derivation earlier in the average power, that then the average power will be equals to half of the maximum current squared times R, or also half of the maximum voltage squared divided by R, the same. And this this power average, the average power should be the same with equivalent with the DC. So it means then the effective current will be equals to, since here we compare here the effective the instantaneous power in DC will be just I squared times R, and in the sinusoidal it is equals to half Im squared times R. Then we know that the effective current I squared here equals to I squared and Im squared times half here. Okay, so the effective current for sinusoidal current will be equals to square root of half times square of the maximum current. Then this is the derivation. If the current is periodic with a period of T, then the average power, actually this is we have derived. The average power within that period equals to 1 over T integral T0 until T0 plus T pt dt. Okay, and then we substitute this formula with this formula, instantaneous power. So this pt equals to R equals to I squared R, I squared TR. Then I squared T is still a function of time, it is still within the integral term, while the R parameter, since it is constant, then we can take it out from the integral, take it out from here, so it becomes R over T integral T0 from T0 until T0 plus T capital, I square T dt. If the current is DC constant, then we know that this is constant, right? IT is a constant with time, doesn't change with time. So it means it equals to IDC. So the integral over from T0 until T0 T will be I squared DC times T times large T. Large T then divided by T, it cancels each other. So the average power for DC current will be equals to R I DC squared, like this. So then the effective current will be when the average power equals to the DC power. So the effective current will be equals to 1 over T. Here integral from T0 until T0 plus T I square T dt. This multiplied by R. So from here, then the effective current equals to this, the right hand side being squared, being square root. Okay, so the effective current equals to the square root of 1 over T integral the mean square. This is basically the mean square. The 1 over t integral from t0 until t0 plus t, I square t dt. So this is the square. To divide it by t, it becomes mean, and being square root, it is become root mean square. That is the origin why effective values is called as root mean square value, RMS. Okay, because the formula is derived from the square of the parameter I square, then its mean over the period, which is 1 over the t, 1 over t, the period here, integral t0 until t0 plus t, then we take root of that value. And that's why it is called as RMS value, root mean square value. So this definition is valid for any periodic signal. So not only sinusoidal, but any periodic signal with a period of t. For a sinusoidal signal, when either voltage, current, or whatever, xt equals to x magnitude, or x maximum cosine omega t plus theta. Yeah, the effective value, if we have derived that the average power value equals to PAV equals to half xm square, like like this, for example, then the effective value here, I square, I effective square equals to half of the Im square. And the Im, the x version could be x, equals to square root of this. So that's why the effective value for any sinusoidal signal xt, xm cosine omega t plus theta equals to xm divided by square root of 2 from this derivation also. For sinusoidal case, the average power equals to half times Vm times Im cosine theta v minus theta I. Yeah, we have derived this in the previous section. So the average power will be equals to Vm here, then so Vm here will be equals to V effective, yeah, times square root of 2. Im here will be equals to I effective times square root of 2. Okay, so as a result, then P average equals to half times square root of 2 times square root of 2 equals to 2. And the 2 here will cancel each other with this denominator 2. So the P average will be equals to V effective times I effective cosine theta V minus theta I. Okay. Let's try some examples here. For example, here we have this kind of voltage waveform. Compute the RMS value of this waveform. So use the formula of RMS, yeah, the value of x RMS square root, root mean square. Remember, root mean square root. The mean of this value will be 1 over t integral t0 until t0 plus t. The mean of the square of the signal, which is x squared t dt. Okay. So within one period, the period here is 3 seconds. Then here basically it consists of 3 regions. From 0 to 1 second, it increases, yeah, from 0 to 4 volt. So basically the function is 4t from 0 to t, from t equal to 0 until equal to 1. Then from 1 to 2 seconds it is equal to 0. From 2 to 3 seconds it is equals to the negative of this, yeah, negative 4t minus 2, because here now it has it intersects the y-axis, the v axis, the voltage axis at plus 8 volt. Okay, that's why minus 4t minus 2. But basically it is the same, only opposite direction, opposite polarity sign. So then the integral of from 0 until t of x squared or voltage square t dt will be equals to these three regions from 0 to 1 for t squared dt. From 1 to 2 is 0, so basically we do not need to write it down because the value is 0 anyway. Then from 2 to 3 seconds will be equals to integral 2 to 3 for t minus 2 square dt. But since this region is basically the same as this integral is from calculus, we know that integral of function is basically the area that is enclosed by that function. Okay, so we know that this region and this region basically has the same area. So they are equal. Yeah. The integral will have the same value. Only one is positive, the other one is negative. Okay, so then the integral of from 0 to 3 v squared dt could be equals to 2 times. Yeah. But since it is square, then it is not negative anymore. So it becomes positive value as well. 2 times 4 square is 16 divided by the integral of the square is 1 over 3 d cubic, yeah, from 0 to 1. So then we obtain the value 32.3 of this. Okay, then the VRMS will be equals to the square root of 1 over t, the period 1 over 3, yeah, times the value of the integral of the square, yeah, which is 32 divided by 3. So then we obtain the VRMs equal to 1.894. Another example, this is a more common waveform, basically a pulse waveform. Compute the RMS value of the voltage waveform and then use that value to determine the average power supplied to the resistor. Here, the resistor is 2 ohm. Okay, so here the I square, this is a periodic square wave. Yeah, the period is 4 seconds. Between 0 to 2 is positive 4 ampere. Between 2 to 4 seconds, it is negative 4 ampere. And the integral is the same, 16, right? And there are two of it from 0 to 4. Yeah, the integral of IT is 16. The IRMS, therefore, equals to 4 ampere. Yeah, please do your own proof. Yeah, try to prove that the IRMS of this square wave is really 4 ampere. So from here, then we can calculate the average power equals to Ri square. RMS 2 ohms times 4 square. Yeah, which is equals to 16, yeah, times 2, 32 watt. So here is the difference there with in the AC sinusoidal, yeah, with I P equals to R, half of R times I square. Now we use IRMS, just similar like when we calculate power for DC circuit. Yeah, R times I square of IRMS square. So here the XRMS, remember, equals to, you can calculate here, where does it come from, using this formula. So 1 over 4 integral from 0 to 4, x square, 4 square. Another example here. Now this is a sawtooth waveform. However, not completely continuous. There is a value where it has a 0 value here. So the period is also 4 seconds. Okay. The period is 4 seconds. Only from 0 to 2, there is a ramp function. So for the t, yeah, for t, or 2t, yeah, 2t, yeah, 2t. From 2 to 4 seconds, it is a 0. So the VRMS will be equal to square root of the mid 1 over 4, 1 over t equal integral 0 until 2, 2t square. 4 t square, 4 t square, 4 divided by 3 t cubic. Okay, like this, and from 0 to 2, so we obtain 8 over, so this is already divided by 2, so we obtain then 8 over 3 volt. Another example now, here we have a pulse, yeah, a pulse waveform with, but it is from 0 to 2, it is 2 ampere. From 2 to 4 second, it is 4 ampere. Then from 4 to 6, it is 2 ampere again. So we know that the period then is 6 seconds. Compute the RMS value for this current, and then use the value to determine the average power supplied to the resistor here. Resistor has the value of 4 ohm. So if you are confused, you can just use this formula X to calculate the XRMS. Square root mean square. The root of the mean is obtained by 1 over t integral from t0 until t0 plus t square, x square dt, x square t dt. The average power then can be calculated from IRMS squared times the resistance value. Yeah. So as mentioned, the period is 6 seconds. Yeah. Then the IRMS square could be calculated. I square RMS, so without the square first, without the root. Yeah. I square RMS equals to 1 over 6 in the, multiplied by integral from 0 to 2 second, and the value is for 2 square. 2 square means 4. 2 to 4 integral 4 square dt, which is 16 dt. Then again from 4 to 6 is integral of 2 square dt, or 4 dt. So from here we obtain this value 8. Yeah, this is 2 times 4 is 8, plus this is 2 times 16 is 32, plus this is 2 times 4 is 8, divided by 6 equals to 8. So the RMS equal to square root of 8. Okay, so P average is I RMS square, which is basically then 8 times the resistance value, or 4. So the power, average power supplied to the resistor equals to 32 watt. Another example here, more pulse. This has the period, yeah, will be 8 seconds. Yeah, the period is from here until here, because this starts with a new pulse again, similar like this one. Okay, the period is 8 seconds. So I square RMS equals to 1 over t, 1 over 8 seconds. Then integral from, so this value is 0 basically, so you just need to calculate this part from 0 to 2, 4 square dt, 16 dt, and at this part 4 to 6 here, minus 4 square dt, or 16 dt, and basically they are the same. 16 times 2, 32. 2 times 32 is 64, divided by 8 is 8. I square RMS is 8, multiplied by the resistance value is 4. So the power average power supplied to the resistor is 32 watt also. Okay. So I think no difficulties. Yeah. Are there any questions related to the calculation of RMS? Otherwise, let's move forward then to the new concept, the power factor. Basically, I think you have done this, yeah, in your lab practices, yeah, in your lab experiments. So to know whether the power is inductive, capacitive, or resistive, and of course the most efficient one when this resistive part. So here we have the maximum, the current flowing represented as in phasor format as a maximum current with a phase angle I, and flowing through a load, represented by this load impedance ZL, and then the voltage across that load impedance is equal to Vm with the phase angle of delta V. Okay, and the theta I is the phase angle of the current from the x-axis, and theta V is the phase angle of the voltage from the x-axis. And the voltage will be equals from Ohm's law equals to the Z, the impedance times the current. So basically then the phase angle of the voltage will be equal to the phase angles of the impedance plus the phase angles of the current. Theta V equals to theta Z plus theta I. Okay? Because this is a multiplication. And so this theta V equals to theta I plus the theta Z. Yeah. So the theta Z here is the addition to due to the phase angle of the impedance. Okay. So when current leads the voltage, then we know that it is capacitive. So theta Z is less than 0 degree, but larger than minus 90 degree. Yeah, since voltage equals to Zi here, voltage equal to Zi. So when theta Z here is negative, between 0 to negative 90 degree, it means that then the voltage lags the current, lags the current, or the current leads the voltage. It's the same way. The different ways of expressing the same facts, equivalent. When the current lags to the voltage, it means that it is inactive. The circuit is inactive. The impedance is more inductive because then you have a positive theta Z. The phase angle of the impedance is positive between 0 to 90 degrees. Here is positive, so it means then the voltage has larger phase angle compared to the phase angle of the current, or the voltage leads the current, or the current lags the voltage. The similar ways of expressing the same facts. Then the average power is, as mentioned in the previous sections, and can be calculated by power equals to half of the maximum voltage times maximum current cosine the angle difference between the voltage and the current. Or if we use effective value of the voltage and current, then we can express it in RMS, where the factor half here will disappear. So it's just equal to V RMS times I RMS times cosine the phase angle difference between the V and between the voltage and current. So if we look here, that the value of T will be maximum when the voltage is in phase, in phase with the current. When theta V equals to theta I, then the difference between them will be 0. Cosine 0 is 1, right? So the power will be maximum. But whenever there is a difference, then you know that the value of that cosine theta will be less than 1. Okay, less than 1, then the P will not be maximum anymore. The apparent power will be equals to the V RMS times the I RMS. Okay. The power factor here is the power, the actual power here divided by the apparent power, or equals to that phase angle, cosine theta V minus theta I. or cosine theta z. Yeah, theta v here minus theta I equals to the phase angle of the impedance. So from here, then the power will be equals to Vrms times Irms for the apparent power multiplied to the power factor Pf. Again, yeah, the power factor is the cosine of the impedance phase angle theta z, or the cosine of the difference between the phase angles of the voltage and the current. So when we have the power factor 1, as I mentioned, when the voltage is in phase with the current, there is no difference between the theta V and theta I. So theta Z will be equal to 0. So it is a resistive circuit. Okay. When the power factor is between 0 and 1, there are two possibilities. Okay. Either when the theta Z is negative, yeah, that is when theta Z is less than 0 degrees but larger than minus 90, between minus 90 or 90 degree, between minus 90 and 0 degree, which means then the current is leading. Yeah, here, the current leads the voltage, or it is a capacitive circuit. When the theta Z is exactly equals to minus 90 degree, what we will have is the power factor will be equals to 0. Yeah, theta Z equals to minus 90 degree, the PF, the power factor cosine minus 90 degree equals to 0. It happens when the circuit is pure capacitive. On the other hand, opposite to that is when the theta Z is positive, yeah, between 0 degrees to 90 degrees, where you have the voltage is leading to the current, or the current lagging the current lags the voltage, which is when the circuit is inductive. When it is pure inductive, then the theta Z will be exactly the same, equal to 90 degrees when we have pure inductive circuit. Okay, now let's try to implement the power factor theory in an example. Find the power supplied by the power company. Here we have, this is the power company represented by this voltage source. Then this is the resistance due to the transmission line, the transmission cable. And we have the load here. The power of the load is 88 kilowatt. The power factor is 0.707 lagging. Okay, so the voltage is lagging. The voltage lags the current by 0.707 power factor. Determine how it changes if the power factor is changed to 0.9. Yeah. So cosine theta Z equals to 0.707. So it means theta Z, since it is lagging, yeah, and if it is lagging, means the current lags the power by lags the voltage by 0.707 power factor, so it is inductive. Okay. Theta Z is minus 45 degree or capacitive here, because it is minus 45 degree. Then, so lagging here means the voltage lags the current. Voltage lags the current because the theta Z is minus 45 degree. Because with the same power factor, you could have positive or negative theta Z. Okay, then it is determined by this statement whether the current lags or whether the current leads the voltage. Okay, theta Z is equal to minus 45 degree. Then you know that the power equals to the Vrms times R. IRMS times the power factor. So the IRMS here equals to the power, which is here 88 kilowatt divided by IRMS divided by the power factor. So we obtained 259.3 ampere RMS. So the P losses is equals to the I square RMS here times resistance. Yeah, the losses due in the transmission line. Yeah, this I square RMS 259.3 squared. This is actually squared times 0.08 ohm. Yeah, then it is 5.378 kilowatt. So the power of the supply here will be equals to this power losses plus the power of the load, 88 kilowatt. So equals to 93.378 kilowatt. Now, if the power factor is increased to 0.9, okay, then the IRMS will be equals to 88 kilowatt divided by the VRMS, 48 watt volt, 48 volt divided by the power factor 0.9. And then we obtain the IRMS smaller, 203.7 ampere RMS. The losses at the cable will be also smaller because of the smaller current. P losses will be equals to IRMS square, okay, times R, so equals 23.32 kilowatt. So here the losses is reduced by 2 kilowatt. Yeah, 2 kilowatt is quite a lot, yeah, quite something. You can power one house, even more. Then we examine the generated voltage. So here current likes the voltage by minus 45 degrees. So then the voltage of the source equals to 0.08 times the IRMS. This one, the resistance, plus the VL, 0.08 times 259.3 ampere here. With the phase angle of minus the ampere, the current elects the voltage, minus, so this is inductive circuit, minus 45 degrees plus 480 volt. 480 volt is the load voltage. Okay, then the voltage source RMS equals to this, and since it's addition, you convert first this phasor format into complex format. 0.08 times 183.4 minus J, 183.4 plus 480. So this becomes 494.7 minus J, 14.7, or if it is reconverted back into a phasor format, it becomes 495 phasor with phase angle of minus 1.7 degrees volt. If the power factor is 0.9, then the IRMS is 203.7 and with phase angle of minus 25.8 degrees. The voltage source equals to this one, calculated from this one, 0.08 ohm multiplied to the current, the current. So this one is minus 180 PS, yeah, plus 480 volt. Yeah, this is the current, the IRMS. This is in complex format. Similarly, here this is in phasor format, so this is in complex format, plus 480 volt of the loading. Then we obtain the voltage source to be 494 volt with the phase angle of minus 0.82 degrees. Okay. Okay, we will continue again since time is already almost 1 p.m. We'll continue again the discussion on power factor next week. So for now, we conclude discussion today. Please fill in